And then, yeah. All right. Hello, my name is Jason Biggs. I'm here to talk to you about chemistry in the Wolfram language. I'm a developer. Previously I was a chemist. I worked in computational chemistry, got my PhD and did a few postdocs. And when doing so, I did almost all of the work that I did in Mathematica, and I really was able to accomplish quite a bit, like pulling in data from generated from other software and plotting it, doing calculations, simulations directly in Mathematica. And so it really felt like a natural step for me to kind of join the company and try and improve the offerings that we have. And so that's the background. Let's see. So yeah, I'd like to go over just kind of a brief overview of the offerings that we have for chemistry in the Wolfram language, and then in future streams here we can discuss new functionality as it's being added. We can explore some in development work, and I've got a little bit of that in this talk, but for the most part I'm going to stick to reviewing kind of what we have. Okay, so just as a brief outline, we'll go over a history of everything that's been in the Wolfram language for chemistry first, and then we'll kind of go over the different symbolic representations that we have for representing chemicals. And I think that's a pretty interesting topic. Then we'll go over how you can do visualization, plotting in 2D and 3D, a little bit of pattern matching. We'll talk about the chemical conversions that we've added in the most recent version in 13.1. And we'll talk a little bit about feature space plot and feature extraction in molecules. And we'll preview a Packlet that is about to be released on the Wolfram Packlet repository. Okay. Right, so here is the history slide. Starting way back here in around 1989 is when Mathematica 1.0 was released. And in version 6 is when we had chemical data, which gives an interface to an amount of data that has been curated by people who work here. And so starting in version 6, you can ask chemical data, water, molar mass. You can ask for water's melting point, which we should all know from our class, right? Water melting point. So we can ask that. We wait for it to initialize a second. And then, yeah, there we go. 0 degrees C, eggs. I'm really glad that worked. I knew it was going to work. So in version 10, we introduced the entity system in the Wolfram language, which was bringing together all these different data domains which we've developed. And so chemicals are the entity type, and that's now the preferred way to interact with the curated data that is in the Wolfram knowledge base. Soon after that, we we introduced a service connection to outside services, like PubChem is a very important one. It's a repository, a public repository of information holding info on like 97 million chemicals, the last that I checked. And so using the built-in functions here, you can contact their API and get as much information as they have available. So then, starting in version 12, we introduced the molecule as a data structure. And then after that, we kind of jumped off. So I don't want to spend too much time talking about each one of these because we will get to those. I don't want to spoil, right? Right. So a chemical representation. What we mean here is it's a symbolic representation. So we've got a biosequence here, right? And so in this case, it is just a peptide with a single amino acid. Obviously, you can do a let's see. There we go. We can make a more interesting biosequence, right? And that has many more peptides. It's got longer sequence. But in this case, if we just have with a single letter, it represents threonine. So you represent that as a biosequence, and you can immediately convert that to a molecule, right? So if we evaluate this, and then evaluate this, these have different levels of information, right? So if we do input form /@ percent. Right, so we've got, yeah, so the molecule contains all the information. It's got all the atoms that you have. It's got all the bonds. It's got stereo information telling you that you have a chiral center with a counterclockwise atom arrangement. Whereas in the biosequence, it really just records what the sequence. And that really is enough. The information here is enough to go to get this. We can also view it from the lens of the Wolfram knowledge base. So we can take that molecule and we can ask, what is your entity? And here I'll evaluate %13. And so it comes back, this is in our knowledge base as L-threonine. And what, just as a quick here, like what's the point of, well, no, I'll get to those down here. So the knowledge base contains lots of information that isn't necessarily computable just based on the structure, right? They've got the hazard classes, the DOT numbers, drug interactions, partition coefficients. These are, again, more curated data, right? And then finally, we can represent it just as a chemical formula, because sometimes when you're reading a paper or you're talking about a particular compound, you don't know what the bonding information is. You only know what the atoms are, you know, and how many of them are. So you can represent it as just a chemical formula, right? And so if you just have a chemical formula, you can still get quite a bit of information from it. You can find the number of atoms, the mass. Let's see, you can get a string representation of it, the mass fractions. So all of these things at these different levels of representation, and these are all what we refer to as symbolic representations of the molecule object. And then finally, we have this function molecule match Q, which can tell you, does this biosequence match this formula? And in this case, it really does. Right, so we can go a little bit more into detail about chemical entities, right? So these again are they involve calls to the Wolfram knowledge base, where our servers have this curated information. You can ask about the acidity constants, the critical temperature, vapor pressure. And so these are all not things that we could compute from the molecule object directly. Whereas with a molecule, you can compute quite a bit, but let's see, the main point here is that a molecule, there's no limit. There doesn't need to be an entry in a database in order for you to create a molecule. So here, obviously, I'm creating a molecule from water. I'm giving it the string water, and it is parsing that locally on your machine, and it looks up and says, yes, water is oxygen with 2 hydrogens, and then it goes from there. You can ask it for its atom list and its bond list, the molecular mass, the adjacency matrix. But you can also very easily create a molecule that never existed, was not in the knowledge base, right? So let's see. So this was an example where you can this would be heavy water. I mean, that's going to be in the knowledge base, but you could set the mass number to some ridiculous value, or you could put in a smile string for some molecule that is just fairly ridiculous, but it's never been written out before. And so this would be some long carbon and oxygen chain. I would not envy the synthetic chemist that needs to make that, but here in our notebook, we can just make it easy as can be. We can just by typing all of these letters here in this language that's referred to as smiles, which is a line notation. It allows you to, by putting in these parentheses, I'm making a branch structure, so I can evaluate that. And suddenly, I never really get tired of saying this, but the number of possible molecules that you could make is limitless. think it's probably countably infinite, but you'd have to ask other people in the building here about that. Interestingly enough, you can also feed molecule one of these big, long, systematic chemical names, and it will go through and it will parse it. It doesn't make any, it doesn't call PubChem, it doesn't call the Wolfram knowledge base. It sits there and reads this from left to right, paying attention to the branching involved in the brackets, the stereo specifications, the different fragments specified here, and can come back with this molecule. If you wanted to, you could start with that same name and create the molecule, create the bonds, and then generate 3D coordinates for it from scratch, right? By from scratch, meaning this doesn't represent anything that came from a crystallographic database. Nobody did a crystal structure on this. And I mean, to be honest, with a molecule like this, the crystal structure is only so relevant because it's, as we like to call it, it's floppy. There's lots of rotatable bonds in this. So the energy difference between different conformations, different angles in the bonds is going to be lower usually than the amount of energy available in solution at room temperature. So in general, that's what we mean by floppy. These bonds are wiggling, vibrating. But the 3D coordinates that we do generate are informed by real chemistry. They, let's see, the angles, the torsion angles, the bond lengths are all informed by chemistry, and then refined using a force field to a quick minimizing the energy. All that after you just hit molecule plot 3D. It asks it for the coordinates and it generates them. Let's see. We already talked about chemical formulas. So right. I mean, what's interesting about chemical formulas is it allows us to represent some chemical reactions that you might encounter in the classroom, which are just written out in terms of formulas. You have no structures, and so that's where chemical formula is useful. So let's say you know that you want C6H5OH. You want this particular sugar here. And so you can't create a molecule from that because you don't know the arrangement of those atoms, what's bonded to what. But you can create a chemical formula from it. And from that, you can get the mass, the charge. You can even, let's see, is that where we're going next? Okay. You can even, right. You can try and find isomers of it, right? So we'll take this guy and we'll say, find isomers of this. And then we want just the smile string. And then let's just see how many we get back. And so what this does right now is it's calling up to PubChem, the database with 97 million entries, and they say they have 211 molecules with that particular formula. We can do a random choice, right, of find isomers, and then we can molecule plot / add, and then let's get 5 of them, right? Yeah, and so I think this one's fairly interesting. What it doesn't do, like I said just now, it makes a call out to PubChem and asks them, what have you got with the formula C6H5OH? What you might ask is, well, could you generate all of the isomers with that particular formula, all possible chemical structures? And that is something that I'm working on. There are applications available which do this, and I'm trying to write a Packlet that will go in the Wolfram Packlet repository that will allow you to generate all of the isomers. But that will be available sometime in the next month or so. All right. So now that we've got representations for biosequences, molecules, entities, formulas, we can start talking about a chemical reaction. Right, so we can look at one of these reactions you might find in in a classroom, right? So you've got sulfuric acid and zinc hydroxide. Acid plus base goes to salt plus water. You can, so this is your symbolic representation of the reaction. You can ask it for its reactants, its products, the counts therein. You can get a displayed form of it. This is interesting. There's lots of room for expansion in this direction, but this is what we've done so far. So now I've already shown you molecule plot, but there's a little bit more that we can do. So again, we can create a molecule from a systematic chemical name, the IUPAC, the International Union of Pure and Applied Chemistry. You can create a molecule from an IUPAC name, and then feed that into molecule and give it and ask it for the plot theme. You can show all of the atoms, all of the hydrogens explicitly, but that's not what we normally do. Normally, let's see, I can go ahead and expand this. Normally, if you look here and you see that there's a carbon, there's no C there because you know that if there's no letter, it's a carbon. And we know that this guy has a double bond and a single bond coming off of it. So you can infer the fact that there is also a hydrogen. So we just don't draw it because it makes the drawings far too busy and hard to read. You can give it a plot theme to emphasize the fact that part of the molecule is aromatic. We can, as we said before, you can generate 3D coordinates for it rather easily. And then unlike in 2D and 3D, we almost always want to show the hydrogens because they're a part of the structure, right? But you can also, let's see, so we've got M up here. You can obviously also give the same plot theme of heavy atom to leave off the hydrogens. And you can also, let's see, combine these. Combine your plot themes. Right. And then you can also highlight particular atoms. You can ask it to highlight so in this case, we're highlighting molecule M, and I want to highlight atom 9. And I also want to highlight bond between atoms 2 and 5. And then I want to highlight any oxygen atoms. And so there we go. Let's see. No, we can definitely not protein fold. I mean, so let's see, you can get a folded protein from the protein data bank, right? And you can import the PDB file or the MMCIF. Folding proteins yourself, we've been looking into that, and it's not trivial, right? It's not like the machine learning where like image generation, where you can just type in a frog playing golf in the mountains, and nowadays it can give you this beautiful image of a frog playing golf in the mountains. Whereas with this protein folding, so essentially you can give it a sequence, right, and it can give you 3D coordinates for it, but it doesn't store everything in these internal matrices and just predict it from the structure. It also has to have basically the entire protein data bank alongside it, like on your disk, because it's going to look at the sequence that you gave it, and then it's going to search the data bank for other similar sequences, trying to find overlap. And then it's going to find these motifs, and it's going to figure out the 3D structure in your local copy of the data bank, and then try and apply those to the sequence that you gave it. So yeah, we are looking into that, but it is not trivial at all. Right. So recently we improved the molecule plotting functions to handle atom labeling. So you can say you can label each atom by its index. You could let's see. You can specify the labels here. Those are a little small, actually. So I might say style this guy font size goes to 17, right? Yeah. So in that way we made the labels a little bit bigger. You can specify actually a property here, right? So we get atom labels goes to, let's say, orbital hybridization. Nope, right. Molecule property. Right, and so there we see that hydrogen atoms are not hybridized, so we label those as just being S, whereas the oxygen is an sp3. We can also so this is a common thing that you see in diagrams in textbooks, is to label the stereocenters by their chirality, S or R. Yeah. So let's see, here's an example, taking a TNT and then labeling every carbon or nitrogen atom by its oxidation state. So you can see the syntax here is really nice. You give a pattern on the left-hand side and then a property on the right. And it labels, as you see, this the nitrogens are all in the +3 oxidation state. Some of the carbons are, whereas carbons range from -3 up to +1. You can do the same thing in 3D, right? Yeah. So we also have a lot of functions for pattern matching, right? So we've got find molecule substructure, molecule contains Q, and I mean these are all kind of based around molecule patterns, right? So here we can say, does this molecule, which is benzene, match the pattern? And here you need to speak a particular kind of language called smarts, which is what this pattern is saying is you have one aromatic atom that's bonded to another aromatic atom that's bonded to another, that's bonded to another, that's bonded to another, that's bonded back to the first one that we labeled with a 1. If we wanted to, we could write that out in long form, right? So we could write molecule pattern. So we could say atom blank aromatic atom Q goes to true, right? And let's go ahead and call that aromatic atom, AA. And so then in our molecule pattern we're building here, AA, 1, 2, 3, 4, 5, 6. And then we do a bond /@ right, 1, comma 2, 2, 3. If I were slick, I would remember the language for partitions here, right? 4, 5, 5, 6, and then sorry for this, 6, 1. Yeah. And so this thing that we just typed out longhand is the exact same thing as this, basically. And they both display, right, so slightly differently. So what this means is that these are bonded by an aromatic atom or aromatic bond, whereas here we've specified in any type of bond. So we could have, if we wanted to, yeah. And so essentially, if you know this particular language, this smarts, then you can write some really small and compact patterns. But if you don't, we have a full form language that you can use. Let's see. Okay, so if AlphaFold exposed their API, then I think it'd be a really interesting project to make a Packlet that calls it, and then yeah. So with that kind of thing, you would need to make the call asking them to do the folding, and then you would receive some kind of task back and you need to come back and check up on it. And I really think that that's the kind of thing that would be great for their new Packlet repository. Yeah. So there's nothing too new here. You can look at these two particular sugars, which differ really only in their 3D arrangement and the chirality of the atoms. Let's see. So this one I think is fairly neat, right? So we're going to find isomers of caffeine. So we're going to find isomers of caffeine, and when it comes back, we echo the number of isomers that it found, which is 2,500, and then we're going to select from those the ones that contain. So the second argument to select here is molecule contains Q, and then molecule contains Q has one argument, which means it's being used in the operator form, right? So molecule contains Q of a bond between an aromatic oxygen and an aromatic nitrogen. So what this command is doing is saying download all isomers of caffeine from PubChem again, and then select only the ones with a bond between oxygen and nitrogen that is aromatic. And so out of those original 2,500, 250 match our pattern. And now what we can do is we can take a random sample of those molecules. And that's why we have the seed here. We take a random sample of them and we find their maximum common substructure. And so that's actually interesting enough to look at. Right. So this is the smarts for this particular molecule pattern, right? With this, again, so this is any carbon atom, aromatic or not, that is bonded via a single bond to something that is, and that bond is definitely not an aromatic ring bond, and it's bonded to something that's either a carbon or a nitrogen that has an aromatic bond to another carbon or nitrogen. Yeah, so this is a very interesting smarts pattern. But this was what was returned back by molecule maximum common substructure. So it took those, and I'm going to go ahead and evaluate this. That was okay. So PubChem doesn't always give back the same number of isomers. That's interesting. Okay. So now we still have 240. So this might be a different selection. So we'll go ahead and keep everything the way it was there. So so on the day that I made this slide, we got 2,500 back. Now we're getting 1,900 back. Look into that. Right. So we found the maximum common substructure in them, and then we are plotting them in 3D, highlighting the maximum common substructure. And so here, I think this is fairly interesting. And then finally, you can take those all and align them in 3D. And then, so this uses the function molecule align, which is very useful function for aligning things, but visualizing it in the documentation examples, you end up always, the way to do it is to show the 3D plots all at the same time to prove that they're aligned. And you can see at the space of the 5-membered ring, they are all aligned, but then they're all kind of all over the place for the rest of the molecules. Okay, something new that we introduced, let's see. Right, so so Dante says, how can PubChem API returns different values for the same call? They are an external service. And so, yeah, I cannot really vouch for them. Or I can't really, I don't really have full explanation there. Yeah. Okay, so starting in version 13.1, we introduced a couple of functions to facilitate chemical conversion. So these are things that we have provided in Wolfram Alpha for a very long time. You've been able to type into Wolfram Alpha convert 2,300 milligrams of sodium to millimoles. Well, now we have the ability to do that in the language. So we have another symbolic representation, a chemical instance of, in this case, sodium, and we say how much of it we have. And then that's our first argument. And then we ask it to convert to millimoles. Obviously, we could have done the same thing and asked for kilomoles, right? Yep. So we can do other things that depend on the density. So in this case, we're doing a conversion from 10 milliliters of water, and we're asking how many molecules are in that. Obviously, we can do other volume conversions. More interestingly, we can take find out how many moles of tricalcium diphosphate can be produced from 5 grams of calcium hydroxide when it's reacted with excess phosphoric acid to produce calcium phosphate and water. So first, we start off with our chemical reaction, which if I'm going to evaluate this in place, right? So we have a chemical reaction with no coefficients, right? So this just says calcium hydroxide plus phosphoric acid goes to calcium phosphate and water. So the first thing we do is we balance that reaction using the built-in function reaction balance, which again, a lot of these functions were built with a mind towards chemical education, because we have a lot of people visiting Wolfram Alpha asking those kinds of questions. And so this is our effort to bring that into the language as proper, right? So, okay, so we start off, we balance that reaction, and we see we've now got coefficients here in front of all the species involved. And so then we can take the ratio of the tricalcium diphosphate and calcium hydroxide, and we find that there's a 1:3 ratio. And then we convert 5 grams of calcium hydroxide to moles, and then divide that by 3. And so we find out that our answer that it takes the number of moles of calcium hydroxide that are needed. All right. This one is fairly interesting, right? So we can do a feature space plot. This was introduced back in version 12.3 that these new feature extractors that can take in a molecule and it essentially return back a list of ones and zeros. It converts them into a fingerprint, as you will, right? And so we have these built-in feature extractors, which are based on things that are well known in the cheminformatics community. Atom pair fingerprints have been used for decades, I believe, extended as well as extended connectivity. Topological features is what is commonly referred to as a daylight style fingerprint or an RD kit fingerprint. And we can use these to make feature space plots. And so here is where I want to go off of this notebook briefly and show something that is almost ready to submit to the Wolfram Packlet repository. And so it's being, we're going through the final bits of a internal review. So let's see. The following is a sneak peek. Will not work if Packlet not installed. Right. So I have this this installed deployed to a resource object, and so I was able to install it on this machine. And so I just want to go through the documentation briefly. So the package is called molecule fingerprints, and it has functions for generating individual fingerprints. And so, for example, let's look here at the atom pair fingerprint. Right. So so the way an atom pair works, it's a substructure defined by 2 atoms and the number of bonds in between them. So along the shortest path in between them. So in this case, we're looking at 2 different types of atom pairs. This is an oxygen with a, let's see. So this is an oxygen with with a valence of, no, not a valence of one, a heavy atom coordination number of one, meaning it has one bond to another heavy atom, and then split between with a seven atom path in between. And then we have the same atom pairs, but with 4 atoms in between. And so essentially what you do is you look at a molecule and you generate all possible atom pairs for that molecule. And for each pair of atoms, you assign it to a bit. And this bit can either be a large integer, so essentially you hash it, and that gives you a large integer. And for convenience sake, usually that is then modded to be between 0 and some number, 1024, 2048, something that's convenient for storing these objects as contiguous bits, right? And so when I ask, I'm just going to scroll down here, for the atom pair fingerprint of this particular molecule, I get back a numeric array, right? And I can normal at that. And it's a bunch of 1s and 0s. And so this is essentially what a molecule fingerprint looks like, right? I could have asked for it as a we call it bit vector. And so this is a bit vector data structure. And so those are very interesting. They're not as well integrated into the Wolfram language. So the default is to return back a numeric array. And then you can take that numeric array. Let's see, let's do this, and let's make a molecule caffeine, right? And then I can take the, so what do we call, Jacquard dissimilarity of %47 and %46. And we get the N at that. Oh, capital N. Sorry, this is not my normal keyboard. Okay, so these two molecules here, molecule caffeine and this particular molecule, are 86% dissimilar, is what this says. And so so that's interesting. You can do lots of different fingerprint dissimilarities between molecules. In this package, there is a molecule distance function so that you don't have to first generate the fingerprint and then call for the Jacquard dissimilarity. It just comes out. And here, this is actually what I came here for. In this Packlet, I put a, let's see, SMILE strings for 300 antibiotic molecules as a resource, a Packlet asset. And then I'm calling feature space plot using the atom pair fingerprint defined here in this Packlet. And then I'm telling it for every point in the feature space plot, label it with a tooltip of the molecule plot, but generate it dynamically so that when I put my mouse over the dot, as it is, the plot is generated right now, right? And so it's fast enough that is great. Because if you didn't do that, if you just said without the labeling function here, it can take a while to generate the plots for all 300 ahead of time. So I always think these are kind of interesting, right? So we've got these clusters of over here of similar molecules, and you can, by mousing over, you can see what exactly feature space plot found to be so similar to in them, right? I hope that I do believe that tooltips come across in what do you call it? The Zoom meeting, but you're going to have to verify that. Okay, so in this Packlet, right, there's extended connectivity fingerprints, topological fingerprints, which are otherwise known as RDKit or daylight fingerprints, right? They have their own hashing algorithm, their own set of options. And so really the point of this is that built into the Wolfram language, we have feature space plot and feature extractor. And those provide just a turnkey, like, boom, it just works. But sometimes you want to fiddle with options. Sometimes you want to specify that you want to use a count vector instead of a bit vector, or that you want to include hydrogens in generating the fingerprints, whereas normally you do not. And so you can generate your own fingerprinting function and feed that to feature extractor. And so that's kind of the point of this Packlet. And so it includes convenience functions like molecule nearest and molecule distance. Right. And so, like I said, this is not released to the Packlet repository yet, but I think it's getting very close. Yeah. Let's see. I wanted to include here, let's see. The notebook will be distributed, let's see, my plan was to save it after I've typed in all this own stuff. If preferred, I could upload the unsullied version, but I kind of like to just type as I go, and I thought that stuff might be useful in there. This last slide is a page of resources that my coworker Jason Sonnenberg has put together, where it lists a lot of the resources that Wolfram Alpha and Wolfram language have available. Right, we have a lot of calculators in Wolfram Alpha that you can interact with directly on your web browser. We've got a lot of functions in the function repository. We've got so this last one, software design. That's an interesting link that should be followed here. Let's see. Right. So this was the kind of the start of the Twitch in our company, right? Doing the live CEOing. And so a very large percentage of the functionality I've just shown you was designed, was pitched to the head of the company, and we refined and hashed out the syntax directly on Twitch. So if you're interested in that would be that could be, you might find that interesting. Okay, that's kind of a tautological statement there. So that's the last slide I have in this talk, but I also have, I wanted to show, since this is a research and development, right? I could show something that is being currently developed. So yes, let's make this guy a little bigger. Zoom on up here. So what, so let me, here. So this paper was circulated on the mailing list here at work about synthesis of a Mobius carbon nanobelt. And so so you can imagine a nanotube, right? But this is a belt, and it's got a twist in it. And so these guys actually were able to synthesize a Mobius nanobelt. And whenever one of these papers comes out, I look to see what kind of supporting information do you have? Is it something that we can ingest? And if so, we could upload it to the Wolfram data repository. And that's what we have here. So in their supporting information, they have coordinates, XYZ files, as well as energies and a few other things for a lot of entities. I guess let me go ahead and evaluate this. And then, so what I did was I imported all of those XYZ files and the data that went along with it, and kind of tried to put it into a form that it was ingestible as an entity store. And so then you need to come in and register that entity type. Right. And so we can do entity count, right? Or entity list of nanobelt. And so what's going on here is that they have the final multi-walled, or let's see, Mobius carbon nanobelt 2525. But then on the way there, they synthesize quite a few precursors and different nanobelts. And so all of the information for all of those things was included in the supplementary information. And so I went ahead and added it to this entity store. And so I think these are really neat, right? So this is the final, oh wait, that's a graphics row. I'm sorry, when I have a 3D plot, I always want to turn them around, right? How can you view something in 3D if it's just flat, right? Let's go ahead and make this bigger. So we have this, you can see the twist right there. I haven't done so, but I was thinking it'd be kind of neat to take each six-membered ring, make a hexagon from it, compute the normal vector, and then draw a line coming out of each ring, and then you could watch them watch those normal vectors flip here at the kink. Right. And so so this is just an ingested form of that data that's available to the users for whatever a user would want to do. Here's the properties that they give: the electronic energy, enthalpy of formation, Gibbs free energy, and the 0-point energy. You can query for those for all of the nanobelts, right? And then let's see, every data repository item needs a nice visualization, and so this looks unexpectedly pretty, I think. Doing a word cloud of the molecule plots in there, and then you can plot the energy of the nanobelts versus the atom count, and see here it's seems to be a steadily decreasing function. You can look at the smallest nanobelt that and it's been a little bit since I read it, so it's unclear whether they actually made this. I think this was just a computed structure. But anyway, the plan is to put this on the Wolfram data repository. I'll be submitting it. I should submit it today. It takes a little while for it to be approved, and then also make a community post about it. And now I'm going to turn to look at questions. Yes, it would. I mean, the correlations between the chemistry that we're doing versus the Wolfram Physics project, I do also think that will be really interesting. And especially directions that we might want to go include, I mean, chemical synthesis, right? Like synthesis planning. And so that really speaks to Stephen Wolfram's his mind, the way he wants everything to be. I mean, or not, he wants everything, but sees everything as connected networks, and these synthesis networks, and could be is definitely something he's expressed an interest in, and so we're hoping to go in that direction also. That is all that I had planned to talk about at the moment. Are there any more questions? All right. Okay, well, I want to say thank you to everybody for tuning in, and yeah, I would actually be very happy to do this on a more regular basis. Yeah, shorter ones about upcoming in development work, and yeah, so if anybody has any questions about this that afterward, feel free to ask on community or the Stack Exchange, or just send a line directly to the company. Okay, thank you very much.